Welcome to the tragic and brilliant saga of Gilbert Newton Lewis, the uncrowned king of chemistry. His name is woven into the very fabric of science, from the Lewis structures of water and ammonia to his pioneering work on chemical bonds, valence pairs, and the fundamental laws of chemical thermodynamics. Despite these significant contributions, ultimate recognition eluded him. He revolutionized our understanding of chemical reactions, free energy and heavy water, yet he never received the Nobel Prize. This is the story of his monumental life, the enduring legacy that continues to shape how we visualize atoms today, and the dark, lingering mystery surrounding his sudden death in his own laboratory. Consider the very vocabulary of modern chemistry. Terms like covalent bonds, Lewis acids and bases, free energy, and even the photon itself are not just chapters in a textbook. They are the foundational concepts created by one extraordinary individual. This person didn't merely discover chemistry, he crafted its language and guided a generation of future laureates. Despite his immense contributions to the scientific community, his relationship with the Nobel Prize was marked by an astonishing fact. He was nominated 41 times. 41 times his peers put his name forward, and 41 times he was overlooked. He won exactly 0 Nobel Prizes. To understand this man, we must examine the unique path of a prodigy. His journey began at an astonishingly early age. By the time he was 3, he was already reading fluently. Homeschooled by his parents in Nebraska, he developed a fiercely independent and unconventional way of thinking that would shape his entire career. By the age of 24, he had earned his PhD at Harvard, where he focused on electrochemical potentials. He then made a significant decision to travel to Germany to study under renowned physical chemistry pioneers Wilhelm Oswald and Walther Nernst. However, his journey was anything but linear. In a bold move, he temporarily stepped away from traditional academia to serve as the superintendent of weights and measures in Manila. His restless mind refused to be confined by convention. In 1912, Lewis made a significant move that would forever change the landscape of American science. He left the prestigious Massachusetts Institute of Technology, MIT, for the University of California, Berkeley. At that time, Berkeley's chemistry department was viewed as a scientifically isolated and somewhat backward outpost on the West Coast. However, Lewis arrived with a revolutionary philosophy. He completely rejected ties to industry and insisted on a strict focus on fundamental science and thermodynamics. The outcome was remarkable. Through exceptional administrative skills and unwavering scientific rigor, he transformed this isolated department into a global powerhouse. In doing so, he permanently shifted the center of gravity of American physical chemistry to the West Coast, creating a legacy that would resonate for generations. At the core of his legacy are the 4 pillars of Lewis's paradigm, monumental breakthroughs that redefined physical science. First, he revolutionized chemical bonding in 1916 by introducing the concept of shared electron pairs. Second, in 1923, he transformed the chaotic thermodynamic equations of the 19th century into a universal tool, known as free energy. Between 1923 and 1938, he addressed the complexities of acids and bases, creating a universal framework centered around the acceptance of electrons. Finally, he explored the boundaries of science by isolating pure heavy water for the first time, coining the term photon, and providing a definitive explanation for organic phosphorescence. He didn't just study the rules of nature, he rewrote them. To appreciate his genius, let's examine the 1916 revolution and the birth of the covalent bond. Before Lewis's groundbreaking paper, The Atom and the Molecule, the scientific community operated under an outdated paradigm. Chemical bonding was primarily understood as ionic, characterized by one atom completely transferring electrons to another, often depicted through rigid cubic structures. Then came the Lewis paradigm. He introduced a radically elegant concept, sharing. By sharing pairs of electrons, atoms could work together to complete their stable valence octets. This singular, profound insight shattered old assumptions, led to the electron dot visualizations we still use today, and effectively established the modern structural theory of chemistry. Lewis set out to create a universal framework for understanding acids and bases, building on the work of his predecessors. In 1884, Arrhenius provided a narrow definition, limiting acidity to the presence of hydrogen and hydroxide ions in water. By 1923, the Bronsted-Lowry theory expanded this view by defining acid-base reactions in terms of proton transfer. However, Lewis revolutionized the concept. His definition shifted the focus from protons to electrons. A Lewis acid is an entity that accepts an electron pair, while a Lewis base is one that donates an electron pair. By eliminating the dependence on hydrogen protons, Lewis demonstrated that all Bronsted acids can be classified as Lewis acids, while also revealing a broader range of chemical reactions, such as the interaction between boron trifluoride and ammonia, that previous definitions had overlooked. Lewis's next significant achievement was mastering the complex field of thermodynamics. In the 19th century, thermodynamic laws, such as those proposed by J.W. Gibbs, were often seen as isolated and highly abstract mathematical equations. Many working chemists overlooked these laws because they seemed impractical for laboratory application. Enter Lewis and Merle Randall. In their groundbreaking 1923 textbook, Thermodynamics and the Free Energy of Chemical Substances, they streamlined these complex equations into a unified, practical system. By introducing precise, measurable terms such as free energy, delta G, fugacity, and activity, they replaced the vague concept of chemical affinity. The impact was monumental. For the first time, chemists could mathematically predict whether a chemical reaction would occur. Lewis's genius transcended traditional boundaries, leading him into what we call the polymathic fringe. In 1933, after his student Harold Urey discovered deuterium, Lewis became the first person in history to successfully isolate and produce a pure sample of heavy water, D2O. Years earlier, in 1926, he published a letter in Nature, where he officially coined the term photon to describe the smallest unit of radiant energy. Finally, in 1944, while collaborating with his student Michael Kasha, he solved the long-standing mystery of organic phosphorescence. He demonstrated that this phenomenon resulted from excited electrons transitioning to a light-trapping, metastable triplet state. Even beyond the field of chemistry, his contributions were monumental. Lewis successfully transformed UC Berkeley into the world's most prestigious center for chemistry, effectively creating what could be called a Nobel factory. However, the ultimate irony lay in the very students and colleagues he nurtured. From his mentorship emerged giants who achieved the highest honor in science. Harold Urey in 1934, William F. Gioke in 1949, Glenn T. Seaborg in 1951, Willard Libby in 1960, and Melvin Calvin in 1961. Lewis possessed the extraordinary brilliance needed to mentor a generation of Nobel laureates, guiding them toward scientific immortality. Yet, while he built the engine that fueled their success, he was systematically and heartbreakingly excluded from the Nobel Club himself. Gilbert Newton Lewis was an exceptionally talented chemist, but his abrasive personality led to significant conflicts throughout his career. During his postdoctoral studies in 1901, Lewis managed to alienate his mentor, Walther Nernst. For many years afterwards, Lewis publicly criticized Nernst's heat theorem, labeling it a regrettable episode in the history of chemistry. This criticism earned him powerful and unforgiving enemies among Europe's scientific elite. Additionally, there was Irving Langmuir, who won the Nobel Prize in 1932 for his work in surface chemistry. Langmuir also played a crucial role in popularizing and expanding upon Lewis's own theories of covalent bonding. Lewis viewed this from the sidelines, nurturing a lifelong and painful resentment toward Langmuir for claiming the international recognition and the prestigious award that Lewis believed should have been his. Welcome to the anatomy of a scientific tragedy, the timeline of calculated sabotage. Between 1922 and 1946, Gilbert Newton Lewis was nominated for the Nobel Prize an astonishing 41 times for his groundbreaking work in thermodynamics, bonding, and heavy water. However, a dark history of behind-the-scenes politics consistently obstructed his path. In 1924, Svante Arrhenius wrote a highly unfavorable report for the Nobel Committee, dismissing Lewis's contributions to thermodynamics as lacking in new discoveries. Later, in the 1930s, Wilhelm Pallmeyer, a member of the Nobel Committee and a close friend of Lewis's rival, Walther Nernst, actively abused his position. Pallmeyer systematically submitted negative reviews, concealed Lewis's nomination file, and ensured that one of chemistry's greatest minds remained permanently excluded from science's highest honor. We note that on March 23, 1946, there was the tragic final experiment of Gilbert Newton Lewis. That Saturday morning, Lewis had lunch with his bitter rival, Irving Langmuir, who was on campus to receive an honorary degree. Associates noted that Lewis returned to his lab in a dark, morose mood, playing a bitter game of bridge before beginning work with liquid hydrogen cyanide (HCN). An hour later, graduate student Michael Kasha found Lewis dead under a workbench, with the room filled with lethal cyanide gas. While the coroner officially attributed the cause of death to coronary artery disease, due to a lack of cyanosis, rumors among his colleagues have persisted. Was it merely a sudden heart attack, or did the uncrowned king of chemistry choose to end his own life? We conclude our discussion by addressing a critical question. Why does Gilbert Newton Lewis hold more significance than many scientists who have actually won the Nobel Prize? The answer lies in the impact of his lasting legacy. Lewis didn't merely discover isolated, fleeting facts. He was a fundamental pioneer in his field. By synthesizing thermodynamics, chemical bonding, and atomic structures into cohesive frameworks, he transformed physical chemistry from a descriptive science into a predictive, structural, and thermodynamic discipline. He didn't just follow the established norms of science. He created the foundational principles that shape our understanding of the molecular universe today. We leave you with the ultimate testament to his enduring presence. Take a look around any modern chemistry laboratory or classroom, and you will see that Gilbert Newton Lewis never truly left us. His name is permanently stitched into the fabric of science. Every time a student draws a valence electron dot structure to visualize a molecule, or a researcher applies the rigorous laws of chemical thermodynamics to predict a reaction, they are operating within the universe he built. He may have been denied the medal in Stockholm, but history granted him a far greater prize, immortality. The story of physical chemistry is, and always will be, the story of Gilbert Newton Lewis.